Well, hello. Welcome to webinar number 3, Check for Understanding, in our series about mastery and Rosenshine's principles of direct instruction. So this is me, Tony. I'll give you a brief video shout, but then I'll turn it off because it seems that we can overdo on the bandwidth side and then you'll have dropouts, which I'd rather avoid. So I'm Tony. I've been working on a bit of a passion here, really, trying to create a practical mastery curriculum in science, which is no mean feat. And we certainly haven't got there yet. But as you can see, we are trying to develop a system for getting more students to the point where they can actually understand and apply what they know, which is at least 1 or 2 steps further than a lot of courses manage. And that is taking a lot of thought and time and practice from you guys, helping us work out what the elements are that we need to do this. So thank you so much for coming, because with this is a two-way thing. We show you our thinking and examples, hoping that you can take them and translate them. And we also want you to tell us what you like, what you don't, and how to do it better, because our products are really there to serve this purpose that I think an increasing number of people think is the way to go. So Gemma.
Hi everyone. Yeah, so a long time ago, about 11 years ago, I was a science teacher, and I stopped doing that to work full-time on projects like the projects I've been working with Tony on curriculum projects. And I'm here today working full-time for Mastery Science. So I hope that you enjoy what we've got to show to you this evening.
Okay, so you may have seen this image that I put up to try and show that checking understanding is actually only a part of the deal. The filling, if you like, in a sandwich. The most exciting part, and the bit that you really want to have lots of ideas and solutions for, and we're definitely going to call on lots of techniques that we can show and how the technology can help, but we don't want to give you a false promise that the techniques on their own are enough. We have drawn some of the techniques from this book here, which some of you may have read. Put in the chat if you've got this. Tell us what you think. This is a really good summary of Rosenshine's work, but it is generic, right? It doesn't really tell you enough about what to do in any particular situation. So we need a lot more guidance, and I hope that today's webinar will do some of that. So what's the point of the sandwich? Well, checking for understanding is only a good thing to do if what you've been doing is taking students along a path to understanding. If you happen to be just filling them with information, it's not very likely they will understand. So checking for understanding seems a bit pointless. You can check for recall and retrieval and all that. But if you want to go to that kind of deeper level, and that's what mastery is about, then you need to have actually planned that pathway towards understanding first, because the purpose of checking for understanding, as Sherrington says, twofold. One is the more obvious one, which is to get students to kind of think more and put more stuff into their long-term memory by rehearsing it and retrieving it. For sure, you can keep asking questions that do that, and that's fine. But really, the main purpose that we're interested in here is, are they actually with you? Are they still with you? Are they getting it? You put together a lesson plan hoping that by the end they would achieve that objective, and at some places during the middle you need to kind of verify whether those assumptions are correct and people are getting it. And if you go too far too fast, obviously you've lost some of them and you'll never get to those objectives in the end. So checking for understanding, according to Rosenshine, is a kind of it's a kind of recognition that there's no way we're going to be successful with our ideas about how to teach something all the time. And we need to keep checking in and going, are they getting it? And we need to do that more than just taking the temperature of the room. We need actual evidence, information that's fairly reliable, will tell us whether all or most or almost nobody is actually getting it. So the two of them work hand in hand, but the third part, the bottom layer of the sandwich, is actually as important, because if you find out that students don't understand, well, you could just reteach it. But if it didn't work very well the first time, probably it's not going to work a lot better if you say it louder. So a plan B is a backup, but it's got to be a good backup. So what we're looking at are two plans, and we'll look at those in the context of a really difficult topic, voltage. Hope that won't put off you non-physicists, because we're going to make it really easy. And we're going to show all the techniques and how the technology can impact if you have it. So what does plan A look like? Well, in our view, it takes account of all the research, not just pedagogy like Rosenshine, but the research that tells you what students are going to find hard. In other words, what are the obstacles you've got to get them over so they understand it's not something that's easy and linear, and if you just put up the right slides, they'll get it. With many, many ideas in science, that's not the case, and 30 odd years of research will back that up. So we do need to know what that research tells us. It's not that difficult because a lot of summaries exist. So there's books, there's institute websites, physics website, and here's one that you might know. This is from York University, the BEST project. So that's a combination of diagnostic questions and giving you some kind of sequence to put your ideas in front of the students in a nice progressive way. And we've used those ideas, which are based on, again, decades of research, to put together a whole actual step-by-step teaching plan and resources that you'll see from Gemma very shortly. So what does it tell us? Well, very simply, and I apologize to the physicists here who tell me it's more than this, but I wanted just to make it simple, three things. Voltage is a different kind of property to current, and so students get them confused, and we probably don't do enough to distinguish the two. And obviously they are unobservables, you can't see them, and which makes it even harder. And then secondly, it's not just about voltage as a push. We're trying to get the idea over that it's actually a difference in energy between 2 points. And we want to start using energy everywhere we teach so that eventually this very difficult idea gets understood. And then thirdly, of course, as with many chemistry concepts, you've got this kind of switch between what you can see, what's happening in front of you, and what you're supposed to be mentally processing, which is some sort of imaginary picture of what's going on inside the wires. So pretty tall order. And in fact, some curricula don't even do it at all because, let me see, yes, here we go. It's because it's too hard, they just give up. So here's a TES resource that pretends it's basically simple. That's what you often see, is presentations that assume you can just kind of inject some knowledge and that leads to understanding. Well, it won't happen with concepts like this, we know that. And the other approach from a textbook, which will remain nameless, is to avoid it completely and say, well, that's the job of GCSE, right? But we would say, well, you know, these difficult ideas, you have to introduce them early in a stepwise fashion because things build and there's not much chance they'll understand at GCSE if they have no foundation to build on earlier. And we think we can do it relatively simply and well. So that's the way to go. Now, at this point, I hope what I want to make the objective of this webinar, as well as learning or refreshing your mind on techniques, is to be able to look at your scheme for whatever difficult idea you're coming to next and be able to go, is that plan A? That would be my takeaway question. Are we using plan A? Because if we're not using plan A, then checking for understanding is always going to be handicapped. What are we covering tonight? It is these particular principles, check for understanding, of course, but also plan A and plan B are there to make sure that you maximize your chance of getting this high success rate. And at the heart of it all is asking questions, understanding questions. So I hope that makes for a good agenda. We're going to go through Plan A to give you an example of a topic, and that will make sense of the questions that follow, and that will be voltage. And then we'll go into the techniques, which are all about collecting the evidence to decide if Plan A works and how technology can enhance that process. And then finally, if it doesn't work, Plan B is your backup. So it had better be good to improve the chance of reaching understanding. So there's the agenda, and we'll get into Plan A. Unless there are any questions, Gemma?
No, not yet.
Okay, so here's what Plan A might look like. I hope it is a Plan A with voltage. So where do we start? We're trying to teach the really difficult idea that voltage is related to energy. And we're going to build on the introduction we gave to energy in year 7. Hopefully you'll do this too, that we model energy in some way. It's a kind of substance-like thing, because otherwise you can't really imagine it. So no energy is an energy bar which is empty. I think everyone gets that when they play video games. You get more energy the higher up the bar is. So it gives you a kind of semi-quantitative idea of what energy is. And then what we're going to do step by step is communicate this model we want working in students' heads, that a battery is a source of energy, and that something takes the energy around the circuit, which we're going to use the syringe for. It doesn't have to be a syringe. You might have a different model similar to this, but we want something to carry the energy around, and that something is the current. The syringe represents the current, and the energy is the orange fluid, and that's going to be transferred to something in the circuit. And we're going to try and use this as a thinking model, because it will explain some things that we want to teach later in the lesson about how voltage is shared in a series circuit and how it isn't shared. And in fact, every component in a parallel circuit actually sees the full voltage of the battery. And you can only really do that if you have some kind of model like this. So why do we do this? This is where the Plan A benefiting from the research comes in. We are actually helping students distinguish the two properties by making them very different looking. It's all about visualizing, because energy is so abstract and remote, we need to make it visual. Imaging, kind of dual coding theory, if you like that. Or thirdly, we are going to be switching between this observable phenomenon level and the kind of microscopic level of what's going on with electrons in wires. So it's actually designed backwards for these specific benefits. And in the lesson, we would be covering these 4 ideas. So the energy coming from the battery, how it moves through the circuit, and then what happens in series and what happens in parallel. And I'll just take you through briefly how we do the first 2, because then you'll make sense of the kind of questioning that Gemma will show you the techniques for. So here's the beginning. We introduce the battery again as a way of providing some energy, and it's storing energy in what we call a chemical energy store. So the battery there has got lots of energy, and excuse me, the voltage that everyone knows is a measure of something about the battery is going to tell us at the beginning how much energy the current gets. That's not precise. Later at the end of the lesson, they'll be ready for a proper definition in terms of how much energy it supplies to each amp. But right at the beginning, we're going to try and say that voltage has got something to do with energy. And then we're going to go step by step to build this model in their heads. So there is the basic idea. And we're going to show with real equipment where possible. There's a student sheet here, and we envisage some kind of teacher-student demo where the teacher's actually doing this on a kind of picture of a circuit with a beaker and a syringe, and showing what's happening at the battery and then at the bulb. So we're trying to make this real and concrete and move the energy around the circuit. So you can see that we're kind of, let me show you again, we're kind of switching between what's going on at the circuit and measuring voltage and this imaginary model of what's happening inside the wires. So that's the context for the check for understanding that we're going to show you next, right? So we're taking students through this model, and how do we know whether they're getting it? That is the question. So does plan A deliver? And that's really what check for understanding is supposed to tell us. Any questions, Gemma?
Nope.
Then you're on.
Okay, so I'm going to talk through the filling in our sandwich, which is how do you check students' understanding of what you've just taught them or why you're teaching it to them. So if we look again then back to Tom Showington in his book, he discusses the importance of check for understanding and how to carry it out in the classroom. But it's pretty difficult to do it. So first of all, you've got to get responses from every single member of the class. And you need to get detail about what they've actually understood, their thinking. And so this keeps the students really engaged because they know that they might have to answer. No opt-out. So that's a technique that you question a student. If they get the answer wrong, okay, fair enough, but you need to go back and check later on that they now know the correct answer. Say it again better. So again, the student gives their response and you have to, well, you help them to improve that answer, to add more detail to their answer. Claire's saying she can't hear me. Don't know what I can do about that.
I can hear you, Gemma. I don't know why.
Okay.
You normally say to people, can you reconnect? Is that right?
Yeah.
I don't know what else you can do, but we certainly have had this problem around about this time of night.
Yeah, okay. I'll have to continue then. Think, pair, share. So that's something that's very popular. So you know how that works. Student talks to a partner, they discuss their ideas and then report back to the class. And then the whole class response, which is what this image is showing here, when you get all the students in the class at the same time to show their response. So there are pros and cons for each of those techniques. So we've just used a few criteria here just to have a look at those. So can you answer lots of questions? So obviously that's really important in the classroom. You need to get lots of feedback so you can make sure students have understood what you're teaching them. Does it reveal deep thinking? Some do, some don't. And is it engaging for all? You don't want a technique where you are just focusing on a few students and excluding others for long periods of time, because that can lead to some students disengaging with the lesson. So how do you choose what technique to use? So it really depends on what type of understanding that you're checking. So if you're just checking terminology and facts, it's going to be very simple one-word answers. Then cold call is ideal for that because you can ask lots and lots of questions very quickly, and whole class works as well. So if you're just doing multi-choice questions, they can write a letter on a board or show you using their fingers or some other technique, and you can get a response very easily from the whole class. However, if you're trying to elicit thinking about the main idea, then those techniques aren't going to work very well. So you need techniques where students can give longer answers and describe their thinking. So say it again and think, pair, share are better for that. So if we have an example then from our mastery materials that Tony's already showed you, this is part of what we call enable. So we're teaching the ideas before students go on to explore new ideas. We're putting in the foundations of knowledge that they need at the start of the lesson. So it's really important that we do use check for understanding to make sure they understand all these things so they can continue on in the explore task and build on them. So this question here is very simple. It's just a numerical answer. So you could use a whole class response. They can all put their answer on a card and show it, and it's very quick for you to check that they know the answer 6 volts. And also it's very easy for you to make up lots of different questions on the same theme. So what if it's 2 1.5 volt batteries? Can they work that out? So that's easy to assess, that kind of question. But this question, which comes at the end of the enable, is trying to understand if they understand that main idea that you've been covering in this enable. So do they understand that the voltage across the battery is the same across that one bulb in the circuit? If they don't understand that, they're going to find it very difficult when you move on to talk about voltage in series and parallel circuits. So we've got a poll here. So what check for understanding technique would you use here in this situation? So if you go on to the poll, has it started, Tony?
It has. I'm not sure you can see it. It has started on my screen.
No, I can't. I can't see it. So have a think and
if you can't see it,
say what technique.
Just put what you think in the in the chat if you can't see the poll. It seems to be moving.
Oh yeah, it is. Yeah, I can see it now. Okay, we'll just do that for a bit.
Okay, let's end that.
Okay, and what's the results? Okay, yeah, think, pair, share, most popular with 44%, and then say it again and cold call. Yeah. So think, pair, share, as we said before, is a really good technique to get students to really talk about their understanding and communicate it to a partner and then to the whole class. Obviously, the disadvantage of that one is that it would take you quite a long time to check every single student's understanding using that technique. So I'm going to go on to talk about something that could help you, which is using technology in your check for understanding. So quite a few benefits of using technology for each of these different techniques, but not all benefit with the technology. So the no opt-out and the whole class we think benefits the most. So if we have a look at the whole class, this is quite easy to do with a technology called Plickers. I don't know if any of you use that, but we actually opened up our WhatsApp chat on this earlier this week. And if you aren't a member of our WhatsApp group, I'll put the link on in a minute so you can join, because there's quite a lot of nice discussion going on about technology and teachers giving each other tips. So Plickers came out as a very popular choice. And if you don't know what it is, basically you can use it for multi-choice questions or true/false answers. Students don't need their own device. All they have is a number of cards, and then they hold up the card that corresponds to the answer they think is correct. And then the teacher has a device, and then you scan all of the cards, and it shows you on your device the percentage of students that chose each option. So you can use that to get a response from every single student, and the students seem to really enjoy it and they get engaged with it. So that's Plickers, and you only need one device in the classroom to use that. But obviously there are limitations there, are the types of questions that you can ask. So it's good for the whole class answers. Other technology does, you will need each student to have their own device, which is obviously a big limitation. But you can use technology to create interactive presentations. So the one that I looked at is called Pear Deck, but there are other ones. There's another one called Nearpod, which does a similar thing. So it allows you then to get instant analysis from the whole class on a range of different question types. So what I did when I used this is I just uploaded one of our complete mastery PowerPoints to Google Slides, which was really easy to do. And then you can choose what types of interactive questions to put onto each slide. So if I give you some examples. So for this one about a battery, I decided to do a drawing question. So the students on their device, this is what it looks like, and they can draw that energy bar. So this is really good for displaying their understanding about how you use energy bars to show energy. So they're actually drawing in the bar there rather than just saying, oh, it goes up or it goes down. And then as a teacher, then you can show the responses of the class. So you could flick through every single response and have a discussion. Do you think this one's right? What do you think of this one? How could this one be improved? And the answers are anonymous, so the students can feel confident in answering, and they're not going to be, called up on for getting it wrong. So that's quite a nice technique, the drawing one. There's other ones like this one I showed you before. So this one is they can enter a number, and then you will get on the responses, you will see the spread of the different answers the students put in, so you can see how well they understand that type of question. And you can do multi-choice questions as well. So this is what the student will see on their screen, X or Y, and then you will get a percentage. So very much like the clickers, but a lot quicker because you don't have to scan the whole classroom. And if we go back to a question where they have to write a longer response, and we said that's quite difficult to do without using technology, then this responses, you will get every single response on the screen. So you could pick out some correct answers, incorrect answers, and sort of have a basis of a discussion with that. And students then can actually see everyone else's answer in the classroom as well and compare that to their answer. So I've got another quick poll. Do you use technology tools like this in your classroom? If we go back onto polls, have a quick think about that. Okay, and popular no, but would like to. Okay, and I think in the chat, if we've got any reasons why I like tech, but students don't all have their own devices. Yeah, and in many schools, students might have devices, but they're not allowed to use their mobile phones, or some students might not have them. It just depends on the school having a suite of tablets for the students to use. Okay. So what the whole point of that is basically is for you to get evidence from those questions to tell you if students are ready to move on to the next stage of their learning. So you would use evidence from every single one of those questions and put up a picture of did they get it or not. So if they got it, great, they're ready to move on to the next stage. And in our case, that's the explore stage. They're ready to build upon that knowledge that they've got of the voltage model. If they didn't get it, though, then that's where you go to your plan B. And that's what Tony's going to talk about now.
Thank you. Well, actually, I'm going to stop for a minute because I think this technology question is worth discussing a bit more because there's so many of you who would like to use it if you could. Is it because the technology makes the job of collecting evidence and using it to make decisions faster and easier, or is there something else? For us, that would be the kind of main criteria of whether to use it or not. Does it make that job faster, easier? That is kind of the superpower of technology, to make complicated things easier. And if you have got low-tech solutions that work almost as well, given the costs associated with using the technology and the drawbacks maybe, then maybe the decision isn't actually worth making at all to use the technology, and you can actually get by perfectly well because the pedagogy is more important than the technology. So please do share ideas on that, because I think this is a really interesting topic for discussion. So moving on, plan B. Let's assume then that you taught voltage brilliantly, but nevertheless, quite a significant fraction of your class didn't get it. What do we do next? It'd be interesting to know with the chat, what do you currently do? What is your plan B as opposed to plan J? Any ideas? What would a good plan B look like before we tell you our view, because there may be some better plan Bs out there. Or do we not just have a plan B at all, and we kind of hope that later in the lesson or in the topic, it will all kind of become clear, and therefore we don't really need a plan B? Oh, great. Thanks, Elliot. So we've got re-explaining using a different model. Yeah. Analogies, examples, good. So the point is that you're going to do something different, teach it in a different way. The question is, do you have something already planned? And if you do, that's great. But if you don't, what we are going to do is give you some ideas. So why would there need to be, why is there like to be a difference in whether students get it or not? Because we think students, for various reasons, take different times to make sense of an idea, right? Very few people on one exposure get a difficult idea. The research suggests it's like at least 3 or 4 exposures. So it's likely that your class can be kind of spread out like the proverbial tortoise and hare, based on their prior knowledge, based on their expertise in doing science, and various genetic and environmental influences, which we won't go into. That would mean there's quite a variation in learning time, which you might often call just ability, but really it is more useful to talk about it in terms of how much time do they need to get the idea. So given that, what makes a good plan B? We think, because of that variation, whatever you do has to be differentiated. So if you treat everyone as tortoises and you kind of just re-explain better or with a different model, you might certainly help the tortoises, but what about the hares? They've already got it. And so they need something more challenging. So that's the problem, really, that any kind of explanation that's delivered orally, lockstep, is going to produce this kind of variation, and plan B needs to accommodate that. So we've been trying to design a textbook partly with this use case in mind, because we think that if you've been doing all the oral stuff, and we did this webinar yesterday, and somebody came up with a great question, which was plan A, the oral presentation direct instruction style, followed by plan B using a textbook. The question was, well, why do you have to do it that way around? Why wouldn't you do it the other way around? Well, of course, if your textbook's really good, you could start with the textbook, and then if that didn't work, you go to the oral version. There is no rule there that you have to do it in a certain way. But basically, the textbook, because it allows for students working more at their own pace, if it's well designed, that actually helps this differentiated instruction. So we're working on a book, and this is just a kind of mock-up to show you what the ingredients would be for voltage, in case you happen to have a book that does this. We think most important is that it can go through the idea very slowly, step by step, like we were trying to explain with our slides, and so that students have a chance to go, I've got that, or I need more help. And we do that with a check for understanding question that's embedded with the text. So we call these self-reflection questions. They're to check whether you've actually read and processed what's in the paragraph, and they're similar to that slide question. So if you've got some of your students working on the book, with the book, and you've got these questions with the text, then when a student can't do the question, that's a signal that they need teacher support. And when they've read and processed, then what you want are nice, easy questions that start very much where the students are maybe thinking about which bits of the model. We want to make sure that they do actually know what the elements of the model are and what they represent, and then being able to use the model. So we take it really slowly. And then for the hares, who don't really need all that, we would have something in the book that counts as more application. We would have some difficult questions that make them think much harder, get to grips with this sort of energy thing, and that would keep them going while you're giving support to the others. So that's what we think is a plausible plan B. I'd like to hear from anyone who thinks they've already got a good plan B that's different to that. Do chat. Because that's essentially where we want to stop. So we'd like some feedback, some questions. If you're really brave, you can even put up your hand to speak. From what you've seen so far, what do you think? Do we need to do some more work on plan A? Do you have plan A? Do you need to think more about quality questioning, or plan B? What do you see? Aha, questions. Okay, we'll answer a few questions and then we'll leave you to chat as you wish. So first question from David, and his idea is that he thinks about misconceptions and then designs a plan B. Sure, I presume we've done that kind of before the lesson starts, or maybe you're that good and you can actually make up a plan B on the spur of the moment. Certainly I couldn't do that. Then Anne's question is, reading age for the textbook. Yes, very good point. What we're trying to work on is clearly a reading age that's a little bit below what they would read if it wasn't science. That's the normal general idea. But we also recognize that students have a wide variation in how much they read expository text, and we don't want that to be a barrier. We know that one of the reasons people don't use textbooks is because their kids can't read that way. So there are two solutions. Either you give up and you just do everything orally, but then you're limited to that channel, which is not a good idea, or you teach them how to read expository text, and that's what we're going to do in the book. So in other words, we're going to show them how to make sense of the text structures that a textbook uses, and how to, think about claims and evidence and reasoning and make sense of what is being taught through text. So if we can upskill them, then they'll actually be able to read the book, they'll be able to learn more. And this is what we're going to discuss in the next webinar. Ian says, extra modeling, right, sure. So you can go into more depth, for sure. Practical activities, and as David said, years of experience. So are there any final questions we should answer, Gemma?
No.
So we are nearing the end of this series. We're going to focus, as I said, on strategies for building stronger, more integrated knowledge next time. And some of that would be, we think, to do with literacy. Some of it is to do with helping students develop thinking skills, metacognition, because it's actually your sort of learning engine or your operating system that determines how well you're going to understand, not just the teacher. We've actually got to kind of build students' abilities to make sense of things. So we're going to discuss how to do that next time.